So this is about the half-life. The half-life again is about time. How long or how much time it take for half of the rectangle to rotate. For half of the rectangle left over. So you see some of those level rules. So then for a second order process, the half-life is inversely proportional to both A0 and K. So the half-life can get into some of those calculations. If you know it, it will be very easy to calculate, to identify it. So you have to know when to what to calculate. So for example, there are few problems. If I give you those time and initial concentration, I will not give you the K, I will give you the half-life. Good. So that means you can let those numbers goes out and just plug them out. So let's see, the molecule dissociated, this is the first order, and it has, you can see, I did not give you the, this is straightforward. I'll tell you the rate constant, and you just ask me what is the half-life. Okay? So if for a second order, I must tell you what is your concentration, and then you can figure out what is the half-life. Right? So now, for the first order, it does not tell you the concentration. It will tell you the rate constant. Then we know we don't need those initial concentration. We just like use that equation and Ln2 over the K and find the half-life. Got it? So now you just remember the equation for the T1 half is 0.693 divided by K. Then what unit you get for your half-life? Well, that usually depends on what unit you get, what unit is given to you for the K. Right? For the first order reaction, your K is just like 1 over the time unit. Time unit can be second, can be minute, can be day, years. And if the time unit for your K is 1 over second, it just obviously 1 over second flip over becomes second. So half-life becomes how many seconds? Okay, now you do a practice. This practice work is kind of much more difficult if you do like some other way to find out. Any idea how you find out this? Well, k first. Okay, so then what? You find out the k, then what? What was that?
Do we use the
You can go by that. That's a good strategy. That's a good strategy because this problem is relatively easy. Is even that ask you will see the content will fall to 1/8 of the initial, right? What about I said you reduce your material to like 13.578%. So you don't exactly have those 1/8 or 1/2, right? 1/2 is half life, right? And how many half life? Let's see, 1 half life is a half. 2 half life is what? 1/4. 3 half life. You can go by that. This question you can solve that. So you have 3 half life. Each half life is 26.4. 79.2, right? Right? That's 23.4 times 3. Your strategy is good. But I said, this you can count it out. Okay, so my ace is, what about I said 1/9? 1/9 will not fall exactly on like 3 half life. Alright, so for this problem, you can count out how many half life. So what we did is counting how many. Okay? And so if you want to count it, that's also a very easy way to count. Okay? You just take 1/2 and let's say to the nth power. So this n will be some of those integers. So n equals 1, 2, 3, and so on. Okay? You can worry about that too. Okay? I'll make a table here. So n equals 1, 2, 3, and 4. Let's just try the first 4 half life. Using this formula, so this formula that means 1/2 to the n power. Let me just rewrite 1 here. Okay. So if I put n is 1 in that formula means 1/2 to the first power. You still get a half. You still get a half. Right? What if I replace this n by 2? You get 1/4. 1/4. Get it? What if I replace this guy by 3? Why is it? Because you know how to do those kind of calculations. So you will take the 1 to the third power, you will take the 2 to the third power, you get 1/8. So next one will be what? 1/16. You see, you just you divide each time like twice of the number before. You divide by 2 here, then you divide by 4, then you divide by 8, then you divide by 16. Next time will be what? You divide by 32. Now those just some very nice easy number exactly fall onto some half life. Maybe your 4th half life, maybe your 5th half life. Right? Now, well, your strategy is very good. So, if I tell you this process is first order, when you talk about those how much level or how much relative and at what time, the best way is the most precise way is using that equation. That equation, that means a to the t equals negative kt plus ln a0. Right? So this equation, even though sometimes you feel no, if you tell me wrong, I don't know what is a0. Right? You don't know what is a0. But if I tell you fall into whatever, 1/9, 1/8, 1/3, that means what that means is at over a0 become 1/8. So probably you can, what that means, so that means what? This is 1, Ln1. I'll put that two together. Okay? But anyhow, so maybe I shall give you this equation if I think this carefully. So I will give you this one rather than that one. So you will have this Ln like this one, okay, equals negative kt. And these two the same, but if you think I use the right one, it's a little bit difficult to put together 1/8. You can do that. If I tell you 1/8, you'll put 1 here and then 8 here. If you put them together, what is 1/8? 1/8 means your AT is 1/8 of your A0. So you put 1/8 times A0 divided by A0, A0 comes out. So you pretty much get 1/8 on that side. If I ask you this kind of question, you very good to think about use this equation. Then you will see where I get the k. Half life. Right? In order to use this equation to find out t, you need the k. And let's do a practice if you give the same answer. Okay? So now let's erase this what I write. And I will just write Ln. So this AT over A0 equals negative kt. Okay? And so by reading this pattern carefully, so we identify AT is 1/8, 1/8. 1/8, excuse me for that, I will write 0 outside. Right? 1/A0. That's the question tells you. So how long does it take for your concentration of A fall to 1/8 of your initial? 1/8 of your initial. Right? And you need a K. How can you find out K? From some equation like this, you'll see K will equals Ln2 divided by what? T1 half. So Ln2 become 0.693. T1 half is 26.4. And so let's see. So therefore K equals some numbers. 0.026. Is that right? Okay. So this is K. And now let's plug this number and also this number back into the equation on the top, and then everything we know, you can solve the t. Okay? So we'll replace AT by 1/8 of A0. Right? So that was initially AT, concentration of A at time t. So now we'll rewrite what as the denominator, we call that A0, A0. Any question? How we get that 1/8 A0? What does that mean? That's what I mean. Like you read the question carefully. See here is a fall to that, not reduced by. Reduced by, you do a subtraction and get how much you get, how much left over. If I said reduced by 20%, right, that means you have 80% left over. Right? So you know those word problem like things like elementary school, right? So I think things like second grade or first grade, reduced to or reduced by. Right, so let's keep writing. So this equals negative 0.026, and then we have this t we don't know. Right? and you can find out what is t. Right? So the cancel out on the left side, so you have Ln 1/8 equals negative 0.026 times t. You solve this equation, you will see t equals Ln 1/8 divided by 0.026. 79.2. Very good, yeah. So that's negative 0.026 equals 79.2 seconds, right? Yeah. So it's a little bit like rigorous, straightforward. You never think of how much half-life. Yeah. You like it like a.
I did 0.693 divided by the second 26.4 seconds, which got my 0.026. And then I did ln 1/8 divided by 0.026 without the negative, but I got the same answer, just negative 79.2.
You are checking, but you don't know the 79.2 seconds. This 79.2 seconds is the one you want to find out, so that's the answer.
Yeah, that's the answer.
Yeah.
I got it.
Yeah. So you can check whether the answer is right or not. Yeah. And by assuming you get this one, then you find out what is for example, what is a k, or what is yeah.
I would.
Similar problem.
No, I got the answer, so we're good.
Okay, any questions? Yeah. If you don't have negative, you can get negative 79.2 seconds.
Yeah.
And then you do that.
And receive logic from that.
Yeah, you're back to the fast. Alright, so this table summarize some of those very important, the very common three type of chemical reactions. The zeroth order on top, and your first order, second order. Okay? So when you have time, you can just try to verify all those information. Okay? That's just notice, so these two red line looks similar. It just goes down very quick. Right? But for the first order, you have this y-axis is LNA, right? And there, for the zeroth order, you just go straight to A. And here, the sequence goes up. So as time goes on, looks like you have more and more reacting, right? But obviously, that means the 1 over the reaction is 1 more. So actually, again, your reaction is getting less and less because you use reactant. Alright, any questions? We did a few of also the unit. You can see the unit for the, we did not do that one. We did this one for the second order. We did this one for the first order. Similar, you can do that zeroth order very quick. That's probably that number. That's even easier because what is zeroth order? See zeroth order here, right? And that one step, that reduce your rate equals k. Rate becomes k. That means your k will have the same unit as rate. So what is the unit for rate? The unit for rate is m over second. Practice on those. See those is like the half-life for the first order. Independent A0, there's no A0 here. And here is your half-life, that means you have more than it take longer to reduce by 1/2. And here, if you have more, you take less, because your rate like depend on twice the square of your rate. And there in the middle, the first order kind of out. So. All right, so that's is about this few of those equations. Any questions? Okay, now we'll study the so-called temperature and rate. Okay, so temperature and rate. Generally speaking, as temperature increases, so does the reaction rate. So what really change your rate dramatically is not the concentration change too much. If you increase the temperature, and what's really changing dramatically change a lot is not the concentration. In the rate law is the K. Okay? So we just have those like the July 4th. So we have the if you buy those you want like have a little still like a few days later you still see like the glowing. So what you do, you will put them in the refrigerators, so then you can take them out and sometime later. And in the evening you can show that again. So that means you put it in the refrigerator, so the temperature is lower, so the reaction rate gets slowed down. Okay, so again, this is because what is the temperature dependent? Okay? This is because this is blank, and ask you what is depend on the temperature so much. Okay. And then we know our usual rate law. So we will see our rate equals K times the concentration A dash is just one reactant to some power like M or N. Usually some people just like to say, well, okay, so for every like 10 degrees Celsius increases, your rate increase like double or something. Those just rule of thumb. Depend on your activation energy, depend on how this K, depend on temperature. So we can actually use some of those equations and do like a calculation. See what. So before we get that equation, we have to see some of those theory or models. So in a chemical reaction, new bond are break, old bond are break and new bond are made. And to break the old bond, you need energy. Okay? The energy comes from collision, collide with each other. So that's about this is about like the fundamental or the principle why the rate is temperature dependent. So in general, if you have to do the chemical reaction, you need to break the chemical bond. The collision of molecules is very interesting. So you have to think about how strongly they collide. And they collide, and when they collide, the collision, those collision happen at what site? So for some of those large molecular, some of those part of the molecular is not active. Some other part of the molecular is active. So if the collision of two molecules happen on the two sides, like let's say you have the on the side, two sides, that's not additive at all. And then when they collide, we're not leading to the chemical reactions. And here, see this example here, okay? The so-called orientation. Okay? So the molecule have to have the right or the correct orientation, and not only that, you have to have enough energy. So these are the two important variables. We have to think about from this collision model for the reaction rate. So now how do you know what is the right orientation? You will examine what is your product. Okay? So this is the product. So this is one of the products, this is one of the products. Okay? So obviously you need to produce two like grain together. Right? And produce two grain together, you cannot colliding the one grain, that one right hand, and one of this the other right hand. You cannot take that grain right hand and colliding like somewhere on the right. Right? So those are so-called orientation. Energy, right? That means you approach this together, so you produce this, you have to go through some of those bond breaking and new bond not really produced yet, so you will have some of those intermediate, very shaky, very loose. And so that have a very high energy. So you have to somehow have enough energy to go through that. So you starting with the cleaning, so the cleaning have enough energy, kind of you push the ball, and the ball have enough energy to roll over the like the barrier. Yeah, so if you want to think about how can you roll the ball over like a hill or ground like that, and obviously you have to give that enough energy. Okay? So that enough energy kind of like the collision between the club and the ball. And the energy required for the reactant to climb over the highest point, which means the most unstable, most shaky complex. So that energy called the activation energy. We call that EA. E standing for energy, A standing for activation. So that's the so-called EA. And so just as those common examples, like you saw in this picture. Okay, any questions? Any comments? Okay, now let's see what I use the word the most shaky part is the part your organ like partly break. Your newborn not really produce, so you imagine that kind of some structure, some building structures. So it's really not stable. Okay? So this kind of a diagram is for the reaction coordinate diagram. Somehow I have that part, so this. Let me just move the similar. and this is the foundation. Right. So this kind of diagram is very interesting to read. At the beginning, you might have a little difficult to understand because this is really, really abstract. Okay? So you imagine you have this guy, the right hand, want to change into this guy. What is the difference between your right hand and the product? Is the connection, okay, of this part to that part. You see your beginning, your right hand, the blue one connecting to that. And that is your carbon C. And here, your carbon connecting to carbon. So you have to flip this part around. Okay. So then you imagine at the beginning, you have this molecule here, have some energy, this multiplying. Okay. So then somehow this, from some other molecule colliding with him, okay, and so this bond began to like getting weak. If that bond began to getting weak, initially this C, this end, this C together is straight. So then you can see the binding, so that's not straight anymore. And then binding more, and here it's kind of this carbon is not bonding to anything, it's bonding to the middle of those electron area, electron regions. And that is the most fluffy, most like unstable part. And so just one of the parts in this whole process. And then you can see that gradually that switch, you switch on this side, and then you can see that it goes down, and then that becomes more and more stable. Okay. So now what is your EA? And you know EA, you are starting from your right hand to the most unstable part for the transition state. And then this you can measure how much that EA. Okay. Yeah. So that is how we like usually visualize some of the typical reactions. Okay. Another part from this diagram is the so-called delta E. Okay? Well, delta E for this example is exothermic, which means you're starting from some high energy species and you release some energy, so this species you produce have energy a little lower than what you're starting from. Okay? So now what are those extra energy you're starting from go? You just go to the environment, go to the surroundings. So the highest point in the diagram called the transition state. Okay? So that's representing a point of energy for this reaction coordinate is the highest point. So we call that a point of energy corresponding to the transition state. And then in that there's a species. Okay? Just like you have, we call those chemical species. So this red product is a species, some compound, some substance, right? And your reactant is some of those substance. There, you cannot really like isolate. You see, I want to get something looks like that. So you cannot get that because they're not stable. They can either quickly goes either like forward or backward, and they will never. Probably is even difficult to like somehow like monitor, use like those modern technology to take like briefly a picture or look what it looks like. You sometimes just imagine. And for some of those small ones, those scientists in some of those high-tech research lab or in those universities, they have some of those instruments. You can get some idea. Just depend on what kind of instrument we have. So the energy, again, that energy gap, you see that blue EA, we call that the activation energy barrier. The larger that barrier, and the slower the rate. Your reaction have to climb over a higher barrier. And opposite is true. If the barrier is lower, then your reaction don't have to have too much energy and get over the barrier relatively easy. This, I think we studied this like in chapter 11, in Chem 1. The sort of the Boltzmann distribution of the speed of molecules. So as we learned before, if we have like some of those examples of material, and at a given temperature, you will have the average kinetic energy in the material. And you pretty much can take a calculation and see what is the average speed for all those number of molecular or ion in a sample. And then you know like we have a lot of those molecular or ions. Avogadro number that much. You know, if you have like 18 gram water, you will have 1 mole. 1 mole means 6.02 times 10 to the power 23. So a lot of those molecules, water molecule or CO2 gas in the sample, right? So you can imagine it's not really realistic for all this that much number of water molecules have the same speed of moving. Some of them obviously were moving slower, some of them moving faster. Okay, so then you can measure or calculate what is the distribution. What is the distribution? Distribution, that means at that speed, what is the percentage? At another higher speed, what is your percentage? At lower speed, what is your percentage? So you do a graph, you see like that, right? And so you can see clearly there's like a different speed. Okay? And you can also notice if your temperature increases, okay, and your distribution gets like broader. Okay? Your temperature decreases, you get kind of a sharper peak. So you that makes sense because if your temperature becomes 0, then everything not moving, they all become a delta line like this. Everyone is 0. So then as your temperature increases, then it just gradually become like more and more distributions. What is interesting from this curve, we can learn those sort of the temperature dependent of reaction rate. Okay? So then you imagine if you see that activation energy EA is some cutting line. Okay? But remember that if you don't have enough energy, your power cannot roll over. Right? So that's like the minimum energy. Okay? And that minimum energy you can see representing in this picture is that dotted line. Okay? And these are energy. So energy higher on this side, energy lower on this side. So that means if the molecule have the energy higher than the cutting line, so it is possible they will change into, they will climb over, change into the product. But that also depends on some other like variables. So your orientation, and even though you have that amount of energy, but on the way you get into the top, then somebody like just boom, just knock you to or do like some of the other collision. But so that's so anyhow. So as you can see, if you have the temperature increases and this area, this red line is a higher temperature, right? So if you see the area is pretty much those the larger the area, that means you will have a larger rate. Because there is more all those molecules that can climb over, possibly climb over. So that is very, very important. So at any temperature, there is a distribution of kinetic energy. And also important to notice that your temperature increases and so this curve shifting to the high energy side. Okay, so that we noticed before, right? So as the temperature increases, the curve flattens and broadens. So therefore, at high temperature, a larger population of molecules have high energy. And that larger population of molecules have a high energy, higher than the cutting line. The EA is represented by the two areas. You have the red area where go all the way down to the bottom. Okay? The blue area is starting from somewhere low. You don't starting from all the way on the red. You're starting somewhere like near the middle. That also go all the way to the bottom. Right? So you have a large area, have a small area, and that means so you will have a larger percentage of molecules that can possibly change into the products. So that's a few slides just try to see. So as you increase the temperature, and your population of possibly can climb over the various molecular increases as temperature increases. And then when so maybe like some percentage of those population can really change the product. So then if that increases, the rate increases. So then you find out this fraction of the molecule can be found out through an equation like this. So you will have this the fraction. So how many like 1/5, 1/5, right, or 1/8 of the population. Okay? So that's called F, the little f. E, you know the E we did those calculation, exponent, the exponent, right? And so the power is a little complicated. Okay? So the power, you know, EA is our activation energy, and R is our gas law constant. But the gas law constant depends on what you do. If you do the calculation like pressure, volume, and temperature for those ideal gas, you use 0.08206. So the same time we use in chapter 12 when we have this osmotic pressure. But when you calculate something about energy, even though this R still have the same name, now R is 8.314, not like the 0.08206. Right? So temperature T again is in Kelvin. So this is this equation. So then Arrhenius, he combined that equation and into this equation for K. So now this K is our rate constant. The EA is still the same as before on the last slide, and R is still the same R, T is still the temperature. Now A is the sort of the frequency factor. The definition for this is a number that represents the frequency of collision with proper orientation for the direction. Alright, so if you take the Ln of that equation, okay? Remember that Arrhenius equation on the last slide? Let me rewrite it here. So it's K equals A times E to the power of EA divided by RT. So that's what the initial Arrhenius equation we saw on the last slide. And use algebra technique, we will take the so-called logarithm. So we take the logarithm of this equation, and we will take this Ln, this type of Ln, natural log. While you will see that you do it like carefully, you will see this equation become this. The top equation becomes this. Yeah, I probably misspelled it. So anyhow, if you have this new equation, then you will see that that you are matching this y equals mx plus b. Right? So what that means, if you measure, I think what we did is we are going to measure that in Marvel's lab. We can measure this this k. You still remember what is the k? It's k. Okay? So this k is for the rate constant. Okay? You can measure the rate constant at a different temperature, right? And then you will take the Ln of your k, and so then you will put that in your so you will put that in the y-axis. So your y-axis is not the simple rate constant, is the Ln k. Right? And your x-axis, so this part usually will be your x-axis, so that becomes 1 over t. 1 over t. And okay, next few slides, we will study how to use that equation, and calculating the k, or calculating that E of A. Okay? So we will see some of the problem, and I might give you like a pair of k, and pair the k with t. So I will give you at what temperature, you see what is your k. So we will study like two type of calculations. We will study like how you using that graph. If you have a lot of data, you have a lot of K, lot of temperature, you will take the L and K and graph with one was T, one was the temperature, and you will get a negative slope. Right? Your negative slope will equals that EA divided by R. So from that you can find out the EA. And EA is very important. So if you know EA, and you can get some rough idea. Oh, let's do that. So this is chapter 13. I think we're on 58, right? Yeah. So I think we just finished that. Right. So we will talk about two types of calculation. If we have a lot of K, a lot of temperature, we can.
That's over.
Roof is. No, same as this morning. So if I get there, I don't have here. So now I have to do it a couple of times, and I will get there, and I'll maybe also here. So anyhow, you don't know whether we get here or not, right? Or we get there or not. So. So you see that you have a lot of data, you can do L and K with 1 over T, and the slope, okay? See the slope, I just imagine the slope here is M, okay? And here is this. So just remember that. If you don't have so many K, so many temperature, you can use the so-called two-point formula. And that is very important. I think that I put like one question on the quiz. Okay? And now let's first see how you use graphing. If I have a few temperature, a few K, and so we will see the graph like result like this. And then let's just practice how to find out some of the information, where you use for information like that E of A from this result. So what are E of A divided by R, or negative E divided by R, that equals what? Negative slope. Oh, that just equals slope. Not negative slope. So that just equals the slope. Now let's just replace those numbers. Okay? What is our slope in this equation? From this graph. So negative what? 1.12 times 10 to the 4th. Yeah. And on this side, you still have this negative EA divided by R. And we know R equals 8.314, and it's joule over mole over Kelvin. Yeah. So you just see this number and replace the R by the R. Okay. And you do the calculation. So your EA equals negative 8.314. That the R carry the negative sign, right? And we multiply negative 8.314. Then we have another negative 1.12 times 10 to the 4. And finally, you probably will, let's say, the unit. What are the units? think this slope over have this the temperature unit there that should cancel out, and you should have joule over moles. Anyhow, you change them into kilojoules or something, because the number can become very tedious. So you get 9.31 times 10 to the 4th joule over mole. Joule per mole. And that equals 93.1 kilojoule per mole. So the slope has the temperature K in it, and you see that's why you count out that Kelvin. But anyhow, the number I did not check that unit for the slope at the beginning. Okay, any questions? Okay, so this is one type of calculation. That means we have a lot of K and a lot of temperature. And you can find out EA. Okay? Most of the time, especially on the quiz exams, you don't have the facility to make a graph like that. Okay? So what you do, I might give you a graph and then just extract the information. Just identify the slope and do a calculation like what I just did. Okay. You can also calculate the sort of frequency factor A, right? So if you imagine like that one number called the intercept. So see the equation you get from the graphing. You get 26.8, and you recall that equation from Arrhenius equation, right? And that equals RNA. Okay? And if you don't remember, if you just think about that equation, have those kind of typical exponential decay. So that K equals A e to the EART, right? So this is R, not a K or something, right? So when you take the Ln, and Ln, so this part become Lna, and that part, okay, because these two numbers are multiplied, so you will have the plus Lne of that number, okay? Then you see the Ln and E, these two operations, you cancel out, so very similar, divide and multiply. So you get that number. Okay? And that's why you get the negative EA over R and then divided by T. But you see, okay, so 1 over T is my X. Okay? So what we want to find out here is this RNA here. You get it? Right? So yeah, good. So now here, so this part, and on the left side, you have the RNK. Okay? Now RNK is here. So RNK here. Okay? And this RNA is our intercept. Okay? Or you can see this RNK is our Y. So these two are the same. Right? Because we usually call that vertical axis is our Y. And we can see like we put that RNK there, or we can just call that Y. So now this part, as Amanda said, probably most of you also notice. So this equation here, this term is simplified. That so this you can rewrite as so this ln k is still ln k, and this ln a is ln a, right? So then this ln and e cancel out. So what you get is negative ea divided by r. Now you write them never like a difference. So you will say multiply by 1 over t. Right? So 1 over t, okay, 1 over t is this part here. Is our x axis. Yeah. And then if you have this number and you have an ln a, just one few k like press, few k stroke. Just say type number 26.8, then take e to the power of that. Obviously that will be a huge number, right? 10 to the positive 11. Because a is the sort of the frequency factor. That means how much collision with the proper orientation, with the right orientation. Now, very similar. We have like a few questions. So if we have that last equation, okay, the decomposition of that, use the results of that Arrhenius analysis, predicting the read constant at 298. Okay? So there, again, there's a couple of ways to do that. Okay? And we probably go back to that equation and see what is our slope and what those equations, what are those standing for. Okay? And I think that will give you like ln k equals negative like 1.12 times 10 to the 4 k something, right? Just go back and see this equation. Get it? Okay. So let's say this is this equation. So I'm going to use this equation, 1.12. And 26.8. Okay? That's the next practice is going to use this equation. Okay? So now let's okay. So now this time I would like what Hope did. So I would write ln k instead of like y. Okay? Equals negative 1.12 times 10 to the 4th. So this guy have a unit k. Right? And in the equation you see times x. But what's really x is 1 over t. Right? And then plus 26.8. Okay. So if you have the equation from from the last slide, and now you just straightforward using this equation, using this equation, just make sure you understand this k is not any variable you have. You don't have any number for the k, just a unit. Okay? So here, this means is Kelvin. Kelvin. Yeah.
What is the R again?
What is R?
And it's 8.316.
Yeah. R equals 8.314 joule over mole times K. But this times is in the denominator. So that means you divide by the K. Okay, what's the number? Anyone have a number? For the K. Okay. Okay, see if you recognize it, and 2.07 times 10 to the negative 5. You got that too? Or, so I think that, well, you obviously you can have a lot of different ways to use the information you get from that graph. Okay? I think, yeah.
Oh, never mind. I see what I messed up. I didn't put one negative. Okay.
Yeah, yeah. That's the usual like a mistake. So you need to remember sometimes there's the negative in like the equation. Okay, so what I did here, two way. Okay, so what I write in the red is the way you just go straightforward from the equation you get from the graph. Right? Remember we also extracting some of the information about EA and A. Okay? If you have, if you remember this Arrhenius equation, which is the one on the top. Okay? So that equation on top, you want to get K, which means you have to know what is A, what is EA, what is R, what is T. So all the information we know. So you plug in, you get K. Or like those few steps I write in red. Okay? The few steps I write in red, the equation you're starting from is the equation from the graph.
So it's just rounding is where we go.
Oh yeah, we get 2.07, you get 2.09. Yeah, just rounding. So here you have to use those R, and now you have to use that EA is from the calculation of you have the slope times R times negative R. So don't worry about 2.09, 2.07. So it's the same number. That is the one we get from the last slide. So we know 26.8 is intercept. Now we know that equals L and K. So now we get A equals that number. Right? So solve this problem we have two way, and then and both of them two is from the graph. Right? But if you don't have the graph, I will usually very easy give you the sort of two pair of K. So you will see I will give you K1 and T1, right? And I will give you K2 and T2. I think we don't have to worry about those detailed algebra. Okay? You don't have to worry about, forget about the last few equations. Okay? Those equations just make your calculation easier. Okay? If you memorize this one, so that will be good. Okay? I just did some of those rearrangements. It's a very simple algebra, EA equal to that. And that means if you have some of those equations like that, and you know how to do a program like in a C or C++, and you can use those equations. But for our purpose, We just have like one calculation or two calculation, and we can just plug those numbers in here, and see what we know. And we can do a simple calculation. We don't have to even find out the equation for EA. To consider reaction between nitrogen dioxide and carbon monoxide, the real constant, so we'll say T1 equals 7/K, right? And then if you sign value T1, then the K you will see that K1. Okay? So T1 is 2.57. And M to 91, S to 91. And let's see the other information, right? Another information is T2 equals 895K, and your K2 equals 567 M/1 2/91. Just like a kind of another information from unit of K. So we know reaction is what order. This reaction is what order. Just by examining the units of the real constant K1 and K2. Second order. Very good, very good. So this is the second order. So then you will use the two-point formula. Okay? Let's see the two-point formula. I think that looks like that. K1 over K2 equals EA divided by R. 1 over no, I forgot T. That's T2 minus 1 over T1. Right? So when you remember, you have that constant. R equals 8.314.
The last slide says K2 over K1.
Then we will switch the temperature. Okay? So now you remember, if I write K1 on the top, and I will have the T2 here, the first one. Right? So now, you just plug those numbers in. So we have 2.57 divided by 567. That's wow. That's like how many times? Like 200 times faster, right? That's a dramatic change. So you will see that become ln equals EA. You don't know. R is 8.314. And now if you carry the unit, and you will get the unit right. Okay? So now let's carry the unit. And that doesn't matter the unit of K because you have K1 or K2 that cancel out. Okay? So I will not rewrite those units in these two because they cancel out. These are the same. Get it? So this is Joule over mole over Kelvin. And then 1 over T2 is 895. Minus 1 over T1, 701. Right? So then both of them have the Kelvin in it. Carolyn here. And this Carolyn will come out. You agree? Okay. And this is there's these two terms together. Okay. Now let's calculate what is this left side. You just simply take the 2.57 divided by 567, and then you take the LN. Okay, so the left side becomes negative 5.396. So the right side, we have the EA on the top. A little easier, you just multiply the R over, right? Well, let's keep that one more step, okay? So this become 8 upon the 314 joule per mole. Okay? So now you have this 1 over 895 over 701. Okay. What's the question? Any question? You need to practice. You need to practice this type of calculation because this will be on the quiz, right? Yeah. So I will make the quiz time labor like more time. Right?
Are we gonna be able to have like any type of cheat sheet or anything for these types of formulas?
For the on the exam?
Not the final exam,
For the exam next week
yeah,
test?
yes. And
I-
they're so long, and there's a bunch of different types of the same equations. It's a lot.
Could we go get
From
confused?
what I know before, if I let you do that, it's not really. I did not see the result difference. Yeah, some semester, I think I tried one semester, it's not really make it the grade better. Yeah, it's really, never mind. If you try, you will just spend a lot of time doing that, you don't have time just do do those practice.
Maybe think about it.
Yeah. Yeah, just typical those questions we do like in the lecture notes and then the quiz. Yeah, I did one in one of those semesters. I think last year in the spring or in the fall semester. Yeah,
Like writing, writing on the board.
writing on the board. You mean doing on a lecture?
The equation.
Equation? I think so. As I said, you spend like time on that. If you don't try to memorize it, sometimes you will memorize it. Just like if you don't try to listen to something, right? If somebody talk about something in the hall, you hear it. If I talk something, you try to pay attention, then you lost your attention, right? Alright, so you see the calculation, so you have this negative number, and you will get also negative number from the right side, so all those come out, right? So we have a negative 5.396. Okay. Now let's just multiply this by over, okay, times 8.314, which has a unit joule per mole. Okay. Now on the right side, so let's keep that number. Now we just calculating these two by subtracting. Okay. So 1 divided by 895 minus 1 divided by 701, and you get negative 0.00309. Am I right? Okay. then you divide this number out. So finally you get an EA. EA is 5.396 times 8.314 divided by that. Divided by this. So you get 145,084 joule per mole. Any question how we get this 145? No question? Okay, good. And then you can change the joule, usually the should be kilojoule, okay, for the EA. Okay? So then just one more step. So this becomes 145 kilojoule per mole equals EA. I think that's, so this was one of the typical problems, okay? The so-called 2.4 of the Arrhenius equation. Okay? You don't have to use that amount of points and do a graphing. What you need is only 2 points. And vice versa. If I don't give you all the K, but I give you the EA, and I give you 2K and 1T, you can find out the second T. Okay? Or I'll give you the EA and 2T and 1K. You will find out the second K. You don't have to memorize any equation. You just memorize this equation I write here. Because this equation has 2K and 2T and 1 EA. Just use algebra. Probably just plug those numbers in and do like first very quick calculation. Some of those numbers can group it together, and then just multiply and divide. That's very simple algebra. So the final answer are the same. We in the middle step, you might get on this side you get a positive number, negative number, right? That is okay because that depends on like where you put the K. Do you take the like the L and K2 and K1? And nobody says you that is K1, that is K2. You assign them like that is K1, that is K2. Just make sure you just if that is K1, then you know where is your T1. Okay? So you just simple calculations. Now you do a practice. So we don't even like specify the problem clearly. I just tell you use last example, last problem, and each of the two temperature to predicting the read constants at 525. Well, now let's choose one temperature. So let's say, do you remember that one temperature? 701. So T, let's call this is T1 is 701. Then your K1 is what is that? 4.5 something. You remember? What is the K1? If temperature 701, 5.6, 2.56, 57. Yeah. 2.57. Okay, so let me write 2.57. Okay. And if you call 701 is your T1, or make sure you change them into Kelvin. Okay. Make sure that should be in Kelvin. If we give you like Celsius, you have to change them into Kelvin. So therefore, we have our T2 equals 525 K. So the unit for the K doesn't matter. That will kind of out. So we have M to the negative 1, S to the negative 1. Okay, what else do we need? We also need something, because we have this equation have 5 variables. What else do we need? We need that EA. right? So EA is 1, you remember EA? 145. Now I will write the kilojoule, but you have to think about what you use, right? So what do you use? So this is, so right now this is the kilojoule, right? Let me also give you one information you probably still remember. R is 8.314 joule per mole per Kelvin. Okay. Now for this first practice, you probably don't have to worry about the units. All the units in the right units. So that's the unit is right paragraph. Right? So what you do, just so right now just concentrate, plug into those number into that equation. Or you, the units you can separate the EA. Okay, EA. You think about that. I mean, the temperature in the Kelvin is okay. You change the EA from the kilojoule into joules. So that is kilojoule. Now let me give you one equation. 1 kilojoule is 1,000 joules. Okay. So make sure change the EA into change the EA into joule per mole, or you want to change the R into kilojoules. Kilojoule per mole per Kelvin. What do you find?
6.1.
Very good. That's very quick. 6.1 times 10 to the negative fourth. Needed to get that too? Yeah, you two get that? Very good, very good. Okay, let me see the, you pair them out 2.5, so you call that your K1, K2, and then you pair this T1 with that. 7.1, because this 2.5, this 2.5 is our K1. Then you have to switch these two numbers.
Oh, it's switches too?
Yeah. And what do you get, yep. Yes, same.
That's it?
You get it, or we get a 6.1, you get 6.8. So
Yeah.
somewhere 8.314, 145, 7.528. Where is your K? Where is your K?
I took the ring out for
LN, and also have the, no, there's not the LN here. LN on the left side. LN, you have the K, so LN K. I think you can assume one of those K you don't know, you might call that K1 or K2. For the other K you give to you, which other K, what name you use for the other K? You use 701, right? So you 701, what I write there, the K is 2.57. Do you use 2.57?
No, where I use that.
You can use that somewhere. Well, you use somewhere, let's see, you get this number, this become 145,000
Yeah.
divided by this, 9 times this. Now this is 701, which is for the 2.57. So we'll put 2.57 here.
Right here?
Yeah.
Okay.
Okay, so then the K you don't know on the top. Yeah. So do a calculation here, see what you get, and
That's no, I just got
that's just now you get. Show me. So 145,000 divided by that. Okay, now that's times. So you don't have to write that down. Just multiply parentheses. 1 divided by 701 minus 1 divided by 5. Do you multiply by those guys?
Yeah, I did that. I just did, I put them all together. I
So
multiplied.
right now you put them all together?
Yeah, I multiplied all this.
You know both sides. Try again. Let's try this way. Try that's 1 divided by 701. Okay, now minus 1 divided by 525. Very good. Then times 145,000. You still have a negative number, right?
Mm-hmm.
Yeah, times 145,000.
Oh,
One more zero, yeah. 145,000.
This one?
Yeah. Now divide by 8.314. Yeah, very good. So now you will take the e to the power of it. Just see what e. What is your e? Okay. Now to the answer of the last part. The second answer. Second. What's the answer? This is the answer. Okay. Hit enter. So now you times the 256. Yeah, so you see, yeah. Okay, anyone need help? How can we go K? You write easy now, you can just say E. Yeah, E, so E to the power of that negative 8.314. I don't know the number right now, but that's. Yes, perfect.
Where are you at?
Okay. Okay, any questions? You use the other way. If this area K1 or K2, then here will be 1 over T2 minus 1 over T1. See here the T1 will be first, then here will be the T2 first. Oh, okay, good. Then, 145,000.
Yeah.
Okay? Now what do you do the calculation to this one first? You will take 1 divided by 5. You're gonna use parentheses. Okay. over 1 divided by 7 over 1. Then times that. Let's time 1 by 1, let me check the calculation. Times 145,000 divided by 3.74. Now you want to get, so this ordinary on the right side. On the left side, we have that number. So you will take the E of this number. Take E to the power of this number. That was really tight. You know how to get the answer back from the last calculation?
Oh, the second.
Yes, second answer.
Okay.
No, that's what you get. Okay, so that is 11. On the left side, that becomes 2.57 over 6. So Q1 equals 2.57 divided by 9. And that's what gives you number. Okay, so I think what we will do, so what we will like to finish this chapter sometime this week. Right? And prepare for the lab. I think the lab, one of the lab is the lab on the laptop. So maybe tomorrow we'll do the lab on the, not on the laptop, we'll do the lab, the real lab. Okay? Yeah, tomorrow. Did you get that number?
Huh? The, no, it's